Example 3 asks us to evaluate the indefinite integral of x squared times e to the x dx. So we want to use integration by parts again. We're going to let u equal x squared. Then du is going to equal 2x times dx. dv is going to equal e to the x times dx. And then v is going to equal e to the x. So we're going to go ahead and use our mnemonic device. We have ultraviolet, so x squared times e to the x minus the integral of v du, so we have e to the x times 2x dx. I'm just going to go ahead and rewrite this, and I'm going to factor out the 2. On this integral, we're going to need to use integration by parts again, so I'm going to let u equal x, which means du would equal dx. dv, I'm going to have be e to the x dx, which gives us v equals e to the x. So our integral now becomes x squared times e to the x minus 2, and then we want to make sure we put brackets or parentheses, ultraviolet minus super voodoo, and I'm going to go ahead and distribute the 2 now. And then the integral of e to the x dx is just e to the x, and then we don't want to forget our constant of integration. So here is our final answer. In the previous example, we have to apply the integration by parts formula multiple times. There is a convenient way to bookkeep our work. This is done by creating a table. Let's see how. So let's evaluate the same integral from the previous example using this new method called tabular method. So what we're going to do is I'm going to create 2 columns, one titled D and one titled I, where D stands for differentiate and I stands for integrate. So ideally, you want to place the function that has the terminating derivative in the D column, which is in this case x squared, and then the other function in the I column. And what we want to do is in the D column, we want to continue taking the derivative until ideally we reach 0. And then in the integration column, we're going to integrate until we get to the same row as the derivative column. Then what we're going to do is we're going to draw diagonal arrows starting from the top left corner, and then we're going to continue this process until we can't draw any more diagonal arrows. Because notice if I try to draw one now, it wouldn't connect anything, so we stop there. And then along these diagonal lines, we're going to alternate starting with plus, minus, and then plus, and we continue that process until we can't go any further. So you might already see the pattern because we had the answer in the previous example. Now what we want to do is we want to multiply the 2 things on opposite ends of the diagonal line. So I'm going to multiply x squared times e to the x, and then the thing in the middle that designates whether we're adding that or subtracting that. So tabular method tells us that this integral is equal to x squared times e to the x, and then minus, then we're going to multiply 2x times e to the x, and then plus 2 times e to the x, and then at the end we just put our constant of integration. So this is our final answer, and as you can see, this is a nice way to organize things, and it kind of gives us our answer in a quicker fashion. Example 5 asks us to find the integral of e to the x times sine of x dx. So here what I'm going to do is I'm going to set u equal to e to the x, then du is going to equal e to the x dx, and then dv will let equal sine of x dx, and then if we integrate that, we get v equals negative cosine of x. So now we have the integral of e to the x sine of x dx, is equal to negative e to the x cosine of x minus the integral of v du. So notice v is negative cosine of x. I'm going to factor out that negative sign and make that a plus. And then we get e to the x cosine of x dx. I'm going to use integration by parts again on this thing. So I'm going to let u equal e to the x. That's going to give us that du is equal to e to the x dx. For dv, we're going to make that cosine of x dx. Then for v, we get sine of x. So now we have negative e to the x times cosine of x plus e to the x times sine of x minus the integral of e to the x sine of x dx. And I'm just going to copy down the left-hand side of my equation again. So we have this. And you might be saying, oh, look, we have this thing. Do we need to use integration by parts again? Well, if we did that, we'd kind of just get a repeat, because if you notice that this integral right here is actually the original integral that we were trying to solve for. So we're going to kind of do a nice trick. What we're going to do is, because we have this integral kind of on both sides, what I'm going to do is I'm going to add this integral to both sides of my equation. And what's nice now is on the left-hand side of the equation, because I'm adding two of the identical things, I can write 2 times the integral of e to the x sine of x dx is equal to negative e to the x cosine of x plus e to the x times sine of x. And then if I wanted to solve for my original integral, I could divide both sides by 2 and then add c, and this gives us our final answer. So this trick comes up often when we are dealing with the product of two functions with non-terminating derivatives. By this we mean that we can keep differentiating functions like e to the x and trig functions indefinitely and never reach 0. Polynomials, on the other hand, will eventually terminate, and their nth derivative, where n is the degree of the polynomial, is identically 0. An acronym that is helpful to memorize when using integration by parts is LIATE. Whichever function comes first in the following list should be set as u. There are exceptions to LIATE, and it is definitely not a perfect technique. Some of these can be solved by using ILATE. Sometimes something completely different needs to be considered. So again, as you're working on integration by parts questions, know that LIATE is not a perfect method. But let's use it in example 6. Example 6 says to evaluate the definite integral from 1 to e of x times the natural log of x dx. Now, the way that LIATE works is you run down the list and you want to prioritize making u the thing that appears first in the list. So if we run down LIATE, L stands for logarithmic functions, and natural log is a logarithmic function. So in this case, because we have a natural log, we want to try making that u. So I'm going to set u equal to the natural log of x, and then du would equal 1 over x dx. dv is going to equal x dx, and then if we integrate both sides of that, we get x squared over 2. So now my definite integral from 1 to e of x times the natural log of x dx is going to equal u times v, so I have x squared over 2 times the natural log of x, and I'm evaluating this from x equals 1 to x equals e, minus the definite integral from 1 to e of v du, so I have x squared over 2 times 1 over x dx. And notice that if I simplify my integrand, I have an x in the numerator and an x in the denominator, so that should just leave me with x in the numerator, and then also I'm going to factor out a 1/2 outside of my integral. Okay, and then if I integrate that, that's going to give me x squared over 2 times the natural log of x minus 1/2. The antiderivative of x is x squared over 2. And then this entire thing is being evaluated from x equals 1 to x equals e. I'm going to go ahead and rewrite this as x squared over 4, and then we can start evaluating. So this is equal to e squared over 2 times the natural log of e, which is 1, minus e squared over 4 minus, let's see, the natural log of 1 is 0. So I think we're just going to have minus 1/4 here. And then if we find a common denominator here, that should give us e squared over 4. And then if I subtract negative 1/4, that's the same thing as adding 1/4. So this should be our final answer for this example.